Hello, hello.
Sir, out okay?
Few things in the world are more powerful than a positive push, a smile, a world of optimism and hope. Good evening to all the dignitaries, guests, and delegates. With great joy and immense exultation, I feel privileged to extend my warm welcome to all presented here for the first Dr. S. Jerome Das Endowment Lecture. First and foremost, I would like to thank God Almighty for His never-ending grace, mercy, and all His beautiful blessings on us. Mark 11:24 says, "Therefore I tell you, whatever you ask in prayer, believe that you have received it, and it will all be yours." I request the audience to remain silent as we praise God with a prayer song. I request the audience to remain silent as Sunshine is a welcome thing. It brings a lot of brightness. I request Dr. J. Madhavan, Dean of Research, to welcome the gathering.
Good evening and welcome to all. And today is a great day in the history of the Department of Physics. Today we have the first Dr. Jerome Das Endowment Lecture. The chief guest of the day, Professor Sunil Verma, Reverend Father Rector, Reverend Father Secretary, Reverend Father Principal, the head, and in whose name we have the endowment lecture, Dr. Jerome, Dr. P. Raj, the research professor and director, Data Center, Dr. Victor, the president of Loyola Physics Association, the coordinator, Dr. R. Mary, and dear professors and my dear students and well-wishers of Dr. Jerome Das. Good evening to you all. First and foremost, I would like to welcome Professor Sunil Verma. I thank him for accepting our invitation to be here and to deliver the first endowment lecture. Thanks and welcome, sir.
Thank you very much.
In their absence, I would like to welcome Reverend Father Rector, Reverend Father Secretary, and Reverend Father Principal. Reverend Father Rector and Reverend Father Principal have shared their message, and we will be sharing with you also. So I welcome on everyone. On behalf of everyone here, I would like to welcome Father Rector, Father Secretary, and Father Principal. I also welcome Dr. P. Raj, who is currently the research professor and director Data Center. He is instrumental for research in our department. When nothing was there, right, he put his effort and he has guided so far 37 PhDs. Right? He has paid maybe the structure, the entire structure is made by him. We are thankful to him for everything he has done, and on everyone's behalf, we would like to welcome you, sir. Welcome, sir. We would like to welcome the head of this department, Dr. Jerome Das, right, and whose name we have this endowment today, right, and his well-wishers, when after he completes guiding 25 PhDs, they came together and initiated this wonderful venture. On behalf of everyone present here, I would like to welcome Dr. Jerome Das. I would like to welcome Dr. R. Mary, the coordinator, the Loyola Physics Association President, Dr. Victor, the Vice President, Dr. Pradap, the faculty members, the students, and everyone, and all the participants. Thank you and welcome you all. Thank you. And now it is time to felicitate our HOD. I request Dr. P. Raj, who is a research professor and director Data Center, to felicitate him with a shawl. Now I request the Deputy President to come forward to felicitate Dr. Jerome Das. On behalf of Reverend Father Principal and the research of the college, I would like to felicitate Dr. Jerome Das for his achievements. Once again, I welcome you for this great event. Thank you.
Thank you, sir, for your kind-heartedness and your warm reception. I would like to request Dr. R. Robert, Assistant Professor, Government Arts College from N. Krishnagiri, to deliver the dynamics of the endowment.
Good evening to everyone. Is it audible? Is it audible? Anyone, please?
Yes, it is audible.
Yeah, thank you. So good evening to everyone. Yeah, warm welcome to respected Reverend Father Secretary, Reverend Father Principal of Loyola College, Chennai. I am grateful to be a part of this great occasion, and it's my immense pleasure to welcome Sunil Verma, Head Biomaterials and Characterization Lab, Laser Biomedical Application Division, RRCAT Indoor. The dynamic personality and most focused person to deliver the talk in Dr. Jerome Das Endowment Lecture Series. I welcome you, sir. I feel it a great honor upon me to act as one of the dynamics of endowment and be here as a representative of many accomplished men and women who are the product of S.J. Training Workshop. He is an eminent teacher, philosopher, and above all, he is our motivator. His in-depth knowledge enlightened many scholars of the field of crystal growth and nanoscience. I was astonished by his skill. It is a boon for your hall. If you get a chance to have him as your teacher. I was one of those who got it. Why endowment awards are important? Because the college endowment students is a better indicator of the college's ability and invest in the students' knowledge for the nation's future. Dr. S. Jerome Das Endowment Award was created last year by the scholars of S.J. Das by depositing 1,88,500 on the occasion of his 25th scholars who pursued a doctorate under Dr. Jerome Das guidance. This endowment mainly focuses to motivate and promote research and development activities in the Department of Physics, Loyola College by utilizing the interest of the Nucleus Fund for conducting lecture series as well as to motivate the students of UG, PG having excellent academic records. And to a prominent researcher pursuing research will be given a memento and certificate. This endowment not only encourages students pursuing research at present in Loyola College, but also it is decided to encourage shine a limelight on a physics doctoral alumni of Loyola, who are the budding superstars and acting as a light in the academic career for hundreds of young students' minds, who are the pillars of future India. These awards will be given during the Loyola College Valley function of Physics Association. With these few words, I thank you all for having given me wonderful opportunity. Now it's time to flourish as by sharing the first wonderful lecture of this series by Dr. Sunil Verma. Thank you one and all. Thank you.
Principal Loyola College to grace and bless the event.
For the rector, the vice president. He brings with him a rich
Actually, this is not audible.
Yeah, we can't listen to what is being said. Can somebody do something?
I am happy to greet Dr. Jerome. Respected Reverend Father Rector, the Vice President of Loyola College, Dr. Francis B. Xavier, Dr. Jerome Das, in honor of whom we have this endowment lecture, Dr. Sunil Verma, the speaker of the day, the officials of the college, and my dear colleagues and beloved students, good afternoon to all of you. I am delighted to offer my felicitations and greetings on this first endowment lecture of Dr. Jerome Das. First and foremost, I should really thank Dr. Sunil Verma for accepting to be with us today. He brings with him a rich wealth of knowledge and expertise which he is going to place before us. I treat this as a golden opportunity for our staff and students to learn from you, my dear sir, also to network with your prestigious organization. Thank you very much for accepting and for being with us today, sir. I also need to thank all the students of Dr. Jerome Das for instituting this endowment. As for me, instituting an endowment has a threefold purpose. One, it perpetuates the memory of the teacher who rendered a dedicated service, selfless service to his students. Secondly, endowment lectures bring technology and knowledge back to the institution. Most often, we invite experts from the industries and other professionals who bring with them rich I am happy to greet Dr. Jerome Das for his years of dedicated service, academically as a professor, administratively as the head of physics department, and research-wise for having contributed much. My association with him started as a colleague in the physics department. He comes across to me as a soft-spoken person, very much dedicated and loyal to the Jesuit management, and committed his profession of teaching and research. Above all, he is, in my experience, an affectionate person who holds everyone in esteem and treats with respect. His experience in the beginning of his career as a CBSE school teacher has formed him as an enthusiastic teacher who could adapt himself to the needs of the students. In the past 32 years, his service in Loyola He has contributed much to the growth of the institution. Apart from his administrative positions as the Dean of Science and Head of Physics Department, he was also Director of Ignatian Institute of Career Development, forming students for civil services. His membership in Examination Committee as well as in Sports Committee helped him offer holistic formation to our students in Loyola. His global experience, either delivering talks in the Hong Kong and South Korea universities, as well as his sharing of expertise as a member of Board of Studies in various institutions in Tamil Nadu, has enriched his academic and research output in Loyola, Chennai. Loyola is proud of his guiding over 30 doctoral scholars and nearly 50 MPhil scholars and publishing over 200 research articles in national and international research journals, and is serving as a resource person for over 40 national and international conferences, as well as his successful completion of 4 major projects. Consequently, his numerous awards bear testimony to his acumen in research and teaching. I wish him all the best in the future as well. And is serving as a resource person for over 40 national and international.
Today, to enhance the joy, I request Dr. J. Madhavan, Dean of Research, to welcome and introduce the speaker.
I deem it a privilege to introduce one of the best scientists in our country. Professor Sunil Verma received MSc Physics degree in the year 1993 from the Punjab University, Chandigarh. Subsequently, he obtained MTech from the Indian Institute of Technology, Delhi, in Applied Optics in the year 1995, and PhD from the Indian Institute of Technology, Kanpur, in 2007. He is an alumnus of the National Institute of Advanced Studies, Bangalore, where he underwent a specialized course in the area of science and technology management. For 1 year, from January 1995 to December 1995, he was project scientist at the Center for Biomedical Engineering, a center jointly run by the IIT Delhi and the AIIMS Delhi, where he worked in the area of development of fluorescent-based optical technologies for biomedical applications. Since 1996, he is working as a scientist at the Raja Ramana Center for Advanced Technology, we call it as RRCAT, Indore, a premier R&D institute under the Department of Atomic Energy, Government of India. In the last 2.5 decades, he has worked broadly in the area of material science and optical engineering, and more recently in the area of biomaterials development for biophotonics application. Currently, he is scientist G and head Biomaterials and Characterization Laboratory, Laser Biomedical Application Division at RRCAT, Indore. Simultaneously, he holds a position of Associate Professor in Physical Sciences and Engineering Sciences in the Homi Bhabha National Institute, Mumbai, a deemed university under the Atomic Energy, Government of India. He received the Best PhD Thesis Award in 2007 from the Indian Laser Association and the Professor P. Ramasamy National Award for the Crystal Growth for the year 2019 from the Indian Association for Crystal Growth for his significant contributions in the area of crystal growth and applications. He has more than 180 publications to his credits, including journal papers, book chapters, and conference publications. More than 25 students have completed the dissertation work under his guidance, and several students are currently working under him. He is a PhD thesis examiner of several Indian universities and reviewer for many prestigious journals in the area of material science and optics. He is on the editorial board of the Journal of Crystallization Process and Technology USA and newsletter of a couple of professional societies. He is a life member of several professional societies such as the Indian Laser Association, the Indian Association for Crystal Growth, the Material Research Society of India, and the Indian Physics Association. Sir, we are privileged to have you. Now, it's over to the chief guest of the day, Professor Sunil Verma. Over to Professor.
Yeah, thank you, Dr. Madhavan. Can I start now? Yeah, thank you, Dr. Madhavan for the nice introduction. And it is a great privilege for me to be presenting lecture in honor of Dr. S. Jerome Das, who is not only a personal friend but a great collaborator. So I am really humbled that the invitation which I received from Loyola College principal and the management and the faculty and the students. Now, before I start my presentation, I would like to speak a few words about this endowment lecture and my association with Professor Jerome Das. Myself and Professor Jerome Das share a very special bond, and it was almost more than 15 years back that we met during a conference and we started discussing about science. That was the start of the thing. And slowly that discussion went on, and it became a full-fledged collaboration between me and Professor Jerome Das, and many of his students then of course worked with me, and they are now at very well-placed positions. And I'm very happy to see that now 30 plus, in fact, I saw the list of gems which was sent to me by Professor Jerome Das, that now 33 gems have been polished by him, and they are now shining in different areas and different parts of the world. So congratulations, Professor Jerome Das, on this great achievement. And it is really a very satisfying experience for me to be giving this endowment lecture, first endowment lecture to name. And it's a privilege, I consider, because Professor Jerome Das is a great human being, because I have had a very long, almost 2 decades long association with him. And he is an outstanding scientist. The research publications, are a testimony to that. He is a par excellence mentor to his students. I think Dr. Robert has put it very nicely, right? Those who are fortunate enough to have got him as their guide, they can sort of say more. But I know him personally, so I know that he's a mentor par excellence. And of course, last but not the least, he is a scientific collaborator and a personal friend, which everybody like me wants to have in his life. and I take him as my personal elder brother. Thank you, sir. Thank you for being there always with me whenever I have asked you to be there. And it is my good fortune, I would say, to have traveled some part of my journey, my academic and my personal journey, along with Professor Jerome Das. And I'm sure that we have many more miles to cover, sir, in our wonderful journey together. And with these words of introduction and with these words for our collaboration and my personal friend, I would now like to start sharing my presentation. So I'll just start it, and just let me know if everything is start your. Can you see it, or should I make it full screen? Yeah. Is it, am I audible? And also, can you please, are you able to see the screen?
Yes, sir. Yes, sir. You are audible, sir.
Fine, thank you. So, this Professor S. Jerome Das Endowment lecture, which I am giving today, it's a tribute from my side to Professor Jerome Das and all the faculty and the management of Loyola College. I would like to specially extend my warm greetings to Reverend Father Secretary Dr. A. Thomas, Reverend Father Rector Dr. Francis Xavier of Loyola Institutions, and I see Professor S.P. Sagayaraj, whom I have not met and personally, but I know a lot about him. And thank you, sir, for being there. And all the management and all the faculty and the students of Loyola College. So it's a great day between the two institutions, RRCAT Indore, which is a R&D unit of Department of Atomic Energy, and Loyola College, Chennai. So our collaboration has gone more than 15, 16 years. And this lecture is some sort of I would say, an intermission type of that, because the story continues, because the film continues. And I think we have a lot more ground to cover before we take rest. So this is an exchange of scientific thought between the two institutes. This is, these are the photographs of mine and Professor Jerome Das long back, somewhere taken in 2007 and then again in 2008. In 2007, I was visiting Chennai and I had an opportunity to come to Loyola College because Dr. Jerome Das invited me. And this right side photograph is taken during that time. And the left side photograph, then again we met next year at SSN College during our annual Crystal Growth Conference. So this is the scientific collaboration and personal friendship which is growing stronger with every passing day. Coming to the lecture, the title of the talk is Growth of Technology Important Optical Crystals, Investing Their Growth Kinetics and Device Relevant Properties and Correlating with the Defect Structure. There are many other areas which I work in, but I have specifically chosen this topic because I believe quite a bit of work which I and Professor Jerome Das have done together falls in this category. So I think it would be a very fitting tribute to him that I deliver a lecture which covers quite a bit of that collaborative work. plan of the talk is something like this. Part 1 of my talk would be growth of technology in important crystals for laser, NLO, and detector applications. Part 2 would be techniques for in situ and real-time investigations of the crystal growth kinetics. And part 3 would be defect characterization and correlation with the defect device-relevant properties of optical crystals. So let me begin with the first part. Since we work in Raja Ramanna Center for Advanced Technology, which is a R&D center dedicated to light sources, basically lasers and accelerators. And accelerators, Indus 1 and Indus 2 are the two national facilities which are in operation at our center, which are called synchrotron radiation sources. So we have two major programs in RRCAT Indore. One major program is based on laser sources, and another one is based on synchrotron radiation sources. So our center is mainly dedicated to the study and development of technologies for light sources. And we contribute in that program from the angle of material science and optical engineering. We make materials, investigate their optical properties for the final device applications, and also make certain devices which are then used in certain lasers or in certain other device applications. So these are some of the materials which we usually work in RRCAT. Laser host materials, for example, NdArc and YuO4, titanium sapphires, analog crystals, KDP, DKDP, KDP, lithium niobate, PBO, lithium iodate. And then lithium niobate is also a very good material for lithium, this integrated optics application. Then we have materials for optical data storage. Lithium niobate, if it is doped with iron or iron and manganese, then it becomes a very good optical data storage material. Similarly, barium titanate and BSO. So these are very good optical data storage materials. Then we also work on detectors and sensors. For example, pyroelectric detectors, TGS, right? Triglycine sulfate is a very, very good pyroelectric material which is used in pyroelectric detectors. Similarly, bismuth germanate. So these are some of the materials which are used in lasers or in detectors or in NLO devices. And for high power applications, we of course grow KDB crystals. And then there are some night vision devices, ZNS, ZNSC based materials which are grown either in thin film or in crystal growth form. So right now I am talking about the crystals, but I will not be covering all of these crystals. I will be giving you only a very brief glimpse of some of these materials just as a representative of what we do there. For example, now let me begin with melt growth, which we also refer to as Czechoslovsky growth technique. This technique we use for growing mainly two types of crystals. One is lithium niobate and another is lithium tetraborate. So here I would very briefly tell you what is the principle and how this crystal is grown. In this technique is mainly applicable to crystals which are grown, which are melting congruently. So what does that mean is essentially that material is not decomposing at its melting point, right? So if a material is getting decomposed, then the composition will change if it is grown by Czechoslovsky method. So this method is applicable only to those materials which are melting congruently. And the first step in growing a crystal by Czechoslovsky technique is you have to prepare the starting material. That starting material is what we call as charge. That starting material is prepared by either mainly by solid state reaction method. So in solid state reaction, you have to mix the 2 or 3 or whatever number of molecular compounds are there, and as per the chemical reaction, as per the stoichiometric chemical reaction, and then you have to mix them in water pastel, then keep it in furnace, follow a particular program so that the material is heated up, and during heating that material will react with each other, and finally you might have to follow this heating cycle a few times, and also you have to crush your material so that you get complete reaction is completed and you get the final starting charge. So for example, in case of niobate, you have to starting materials are lithium carbonate and niobium pentoxide. So you have to make these materials react react and form lithium niobate in a solid state reaction method. Once the material is formed, for example, lithium niobate has been formed in solid state reaction method, then you have to load it in a platinum crucible, and then that platinum has to be kept inside a furnace. And that furnace can be either it can be an inductively coupled furnace, or it can be a resistively coupled furnace. In case of lithium niobate, we use inductively coupled furnace, right? And after this charge, that is the platinum chemical loaded in the furnace by keeping that crucible filled with charge inside the furnace, we heat up the furnace, we follow a particular temperature heating program so that it reaches up to the melting point. And we melt. In case of lithium niobate, it is 1250. So we heat it up to 1250 degree. Furnace is slowly ramped up, and the charge is melted. Now once the niobate is completely melted, what we do is we have a seed rod, and at the end of that seed rod is a ceramic rod withstand high temperatures. That ceramic rod is coupled to a crystal Czochralski crystal puller. And at the end of that ceramic rod, we have a lithium niobate seed crystal, which you see out here. This small seed crystal is tied to this ceramic rod, and this seed rod is dipped and is made to touch the melt level. This is the melting charge. This is the crucible which I was talking, and these red dots you see are basically representative of the furnace heating. Basically your heater. Fine. So once you touch that seed rod, the seed rod will once you touch it, and suddenly you lift it up also. But you don't let that seed get detached from the surface, and you will see that because of the surface tension, the crystal is still sticking to the melt level. And then you rotate and pull this ceramic rod. Basically, pull the seed up very slowly, and you will see that slowly the crystal start at the tip of this seed. And then depending upon the rotation rate and the pull rate, the size of the crystal is decided. So we call it necking, and then we call it shoulder, and then finally we get a almost a uniform crystal. And once the crystal has been grown, then finally again raise the temperature slightly, so that the final interface region melt and the grown crystal is detached from the melt, and we take out the crystal. And the crystal looks something. Resistive furnace on the right hand side. This is the seed rod is inside the furnace, and this is having the crucible which I was talking. And on the left hand side you see inductively coupled crystal growth system. This is that furnace. These are our RF sources. Right, and this is the computer system with which this crystal puller is operated. So, and these are some of the crystals which we have grown. For example, we have lithium niobate, pure lithium niobate, then iron doped lithium niobate, manganese doped undoped tetraborate, doped lithium tetraborate, and the applications for which these crystals are grown are different. Right? For example, lithium niobate is a very good integrated optical material, it's a SNG material also, and it's a very good optical data storage. So we use these materials for these applications. And lithium tetraborate, I'll come back to those slides. Lithium tetraborate is a very good radiation dosimetry material. We use it for making radiation dosimetry batches. Now, one of the very important crystal which I want to sort of present here is still being crystal. It's required in Department of Atomic Energy for neutron detector applications. Because being part of Department of Atomic Energy, we have to work on those types of which have applications on ND national ND program. And this making of neutron detector is very important, especially making of fast neutron detector. For example, there are many materials, many ways in which thermal can be sort of detected, but there are not very good materials available for detection of fast neutron. I mean any neutron which is having an energy more than 1 mega electron volt is referred to as fast, right? So usually the methodology which is followed generally if there is no material available for detection of fast neutrons is first we have to thermalize that neutron using some sort of moderators, and then once the material once the neutron energy have been thermalized, then we will use a thermal neutron detector, right? So it's an indirect way of detecting the energy of fast. You have to first thermalize them, and then tell that this was the energy of the electron neutron which we have thermalized. So indirectly you have to do calibration and find those. So very few materials are available which can directly give you a fast detection and still bean is one. And we have been able to grow this material using enrichment technique. And we have crystals of the size of 30 mm diameter and 100 mm length. And you see this long crystal on the right hand side. And these are some of the elements which we have been able to take out. These cuboidal materials. And these materials have been tested for neutron detection at JRE in Mumbai. And also some work is going on some other national laboratories also in this regard. Now. Another important work, and I'm very proud to say that this work was done by one of the very bright students of Dr. Jerome Das. Dr. S. Dinakaran, who now is an assistant professor in St. Joseph College in Tripoli. So he worked with me, and thanks to Jerome Das, who's such a nice and a good student to me to work for his PhD. In fact, he did all his experiments while he was at Cat. Thank you, sir. And I'm sure Dinakaran is doing very well nowadays. So this was the first report which appeared in literature which shows that we can directly grow crystals in the phase matching direction. Usually what we do is we grow a crystal in its natural morphology. This I'm talking about growth from solution, right? So in the previous two slides I had talked about Jagrodsky growth, then I talked about Bridgman growth. Now I will be talking results from solution growth, right? So usually when a crystal is being grown from solution takes a natural morphology, right? But sometimes what happens is when you have to take out a device element from it, the usable volume of that crystal which is finally being used for device fabrication purpose is only a few percent of that crystal. For example, in case of KDP grows in bipyramidal morphology. So it has pyramids on both the sides. This is the C axis of the KDP. And you have A and B axis, normal to these faces, which are 1 and 0 faces. And along this 1 direction, you have four faces. This we call as the pyramidal faces on the Z direction and also in the minus Z direction. And if you have this KDP is mainly being used either for focal cell or Kerr cell effects. Basically, we use it for second harmonic generation. It's a very good material for high power laser applications. So we use this material for second harmonic generation. And in that case, what we do is we have to cut a SHG element from this crystal. So for that you have to make first you have to take out an element which is normal to the phase matching direction so that the laser can pass through this crystal. So what we have to do is we have to first cut this crystal 59 degrees to the Z axis, and then we have to make two normal cuts along this 59 degrees direction. Finally we will get an element which will be shaded portion only device element which is possible from a crystal which is actually of this big size. So the usable volume which you grow a crystal in conventional geometry, conventional morphology, the usable volume will only be around 20-25%. That is the maximum 75% of its volume goes waste. Right. So that's a huge loss, I would say. For a material scientist, 75% of the material which has been grown is not being used for devices. I would say we must think to devise new technologies which can increase this usable. So what we thought was why not use seed directly oriented along phase matching direction, put it inside a cylindrical chamber, and the axis of the cylinder should be the phase direction, and let it grow along that direction. And this cue was taken from the work which Ramasamy and his collaborator Professor Shankar Narayana did, and you now know about this SR technique. Shankar Ramasamy technique of doing crystals. So what we thought was we made a setup. In fact, the student Jerome Das, Dr. Dinakaran, he made this setup in my lab, and I told him that instead of growing it directly in the natural morphology, you should grow it in this way. So he followed that instruction. He made a seed crystal in a conical form. The cone of that seed was basically the direction. And this cone was that put at the bottom of this ampule, and then we allowed this crystal to grow. And then this was the final crystal which was grown after about 10 days. And when cut this crystal, in fact we put this crystal in the laser beam path, and we were able to see the axis of this crystal. When the laser was passing through the center of this crystal, we were able to see the green. So second harmonic generation was generated, and we were really excited. We have proved that now. In fact, we were able to show only the bottom 5 mm has been cut because we needed a flat surface and little bit of 1 or 2 emission from the top was cut. So only 10%. I would say that was. This is also a little more. In fact, what I would say is that the material increased from 20 or 25% to 90%. Crystal was grown directly along direction. The useful volume of the grown crystal was about 90%. So that was a great achievement. We were able to very easily get this work published. Viewers also very I would say encouraging comment on this new technology which was developed. Similarly, and the proof of although we had shown the principle by growing ADP crystal, we thought we should try it and validate it further. So we took a benzophenone crystal, which again it's a very good material, and it again grows in the form of a bipyramid morphology if you grow it naturally. So what we thought was why not try the same thing in case of benzophenone crystal. So the first step one is conventional top morphology. Crystal was top hanging geometry. This crystal was grown, which is a bipyramidal morphology crystal. Then we found out the phase matching direction for this, and these were the phase matching direction. After obtaining the phase matching direction, we decided how to cut this crystal so that we get the seeds which are oriented along the phase matching direction. So if you see, this is the top view of this bipyramidal. In case of KDP, this is a square or a rectangle. Angles are 90. In case of benzophenone, this is a shifted parallel, right? So we cut this crystal normal to x-axis, and finally this whole element once you cut it, you will get this shape, and this shape incident 1064 along this direction, you will get 532 out of it. And we made very small 4 elements from it. Each of these elements was this is the element which we obtained from this crystal, this which we used as a seed finally, and this was tested before we put it inside the fuel for crystal, because we wanted to make it doubly sure that the direction with which we have cut the crystal, which we are assuming to be a phase matching, that actually is a phase matching direction or not. So before putting it inside the growth chamber, we did this trial experiment, and we were sure now that the axis of this seed is now the phase matching direction. And put this seed, you can see the small seed inside this ampule, which is right now, and then this was filled up with the solution. Then then this crystal was grown. And this now you see this crystal. It's 9 centimeter long crystal was grown, and the crystal volume which was usable for SHG application in case of benzophenone. If it is a conventional geometry grown crystal is only 20%. But if you use a phase matching direction seed and put it inside an ampoule, you can increase the usable volume of the grown crystal from 20% to 90%. So this was another example, another way in which we prove that this can be done. These are some other NLO crystals which we have grown. This is a cysteine hydrochloride monohydrate. This is a very good biomaterial, and in fact if you find out literature, it's a very good biomaterial which people require. And we grew this material and images which you see. We also do online real-time imaging of the growth process. So this was the small crystal which we had put. If you see the A image marked as A. This is the starting of that growth. And then every day we used to record this because there was a camera fitted in the chamber. And we used to record our images every few hours, and then I have taken out these images every 24 hours, right? Ramasamy when he was working with me in our CAT, and he has been instrumental in growing four different crystals. TGS crystals. These are different setups which were made during his stay there, and he and we together worked to grow TGS crystals below and above phase transitions. I think you must be knowing that TGS is a very good ferroelectric material. It's a very good parallelectric material. But the problem is that above phase transition temperature, which is at 49.3 degrees, it is parallelectric. So all the uses of TGS are below its phase transition temperature. So what was an self-pooling material. So if you raise the temperature above 49.3 degrees, it becomes parallelectric. But you don't have to put any electric field or remove an electric field. If you cool that material, automatically when it comes below 49.3 degree, it becomes ferroelectric, right? So we thought that why not use this property of this self-pooling material, triglykosine sulfate, and the main motivation for growing this material above and below phase temperature was we wanted to see because the solubility of TGS above 49.3 is very high, and below 49.3 is less. So we thought if we can utilize this high solubility of 49.3, we can increase the growth rate, and we can grow a very large crystal in relatively small, lesser number of days. And then because we are anyway below the phase transition temperature, it will automatically come back to its ferroelectric state, which we really wanted, right? That crystal because all the device applications are in the ferroelectric state. So we thought that okay, if we grow only along above phase transition temperature, then we may not be able to make a comparison. So we thought we will grow TGS above phase transition temperature, and also similarly simultaneously we will grow another crystal below phase transition temperatures. So we did two different experiments on pure TGS doped with 70% of LNI is doped TGS to enhance its ferroelectric properties which are used for IR detection applications. And similarly we also grew TGS above its phase transition and below its phase transition temperature by doping urea, because that also enhances some of these. And these are 6 crystals which were grown, and these crystals were cut and characterized, and their merits were measured. All this work has been published in excellent, outstanding journals. And in fact, these are some of the representative results and some setup which I am showing, which we have been able to grow using both. I showed you some of the work using men, and this I am showing about KDP, lithium paranite, zinc tris. We have worked extensively on ZTS, computationally also, and in experimentally also. Sylvine crystal, phenol, cysteine, hydrochloride, monohydrate, TGS, and all this. Right? So a lot of crystals we have grown using solution. Now that was a very brief discussion about crystal growth for NLO and detector apps. Now I'll come back to the second part of my talk, that is techniques for in situ and real-time investigations of crystal growth. You all know. And those who are in crystal growth, they will appreciate that. Okay, we are growing a lot of crystals. But then, unless and until we really understand how a crystal is growing, why it is taking a particular shape, why that defect is coming in a crystal under some growth conditions, why that goes away when the growth conditions are changed. So we must be able to study the basics of growth, and nothing better than doing some experiments for understanding those growth mechanisms. We all know that there is a dislocation mediated growth. There is birth and model of growth. Parallel growth mechanism, which is basically a dislocation mediated growth. And we also know that there is a flat step and kink model of growth. So we thought if we can do some experiments which can validate these models, that would be very wonderful. So we initiated some activity long back on these aspects, and then because our forte was having some optical techniques, laser-based techniques, so we thought we doing some sort of imaging studies, so that we get the image of whatever crystal is growing, and through these optical techniques. So we use several optical techniques, and these are some of them. So optical techniques for investigating crystal growth kinetics, laser shadowgraphy, convection studies and saturation temperature determination, Maxenter interferometry for concentration imaging of the solution from which the crystal is growing, and also the quality of the crystal. I will show you some interferograms of the crystal when it is growing. Michelson interferometry for surface microstructure studies. Birefringence interferometry for growth rate studies as a function of growth parameter. Tomographic imaging of concentration and convection. Dual wavelength interferometry for thermal and effects. And then finally all these types of techniques have been integrated into a single setup which we now use, and we call it a composite multimodal imaging technique. Right. So to start with, let me briefly tell you about what is shadowgraphy. Shadowgraphy is a technique which has been extensively used in experimental fluid dynamics research. So if you have seen how these companies who are manufacturing sports cars and who are in fact this technique has been extensively used even in rocket launch stations and all, because they want to study the aerodynamics when a vehicle is moving, or when a fast moving rocket or missile is moving. So what we thought was that we want to see what type of convection patterns, what types of flow dynamics is there around a growing crystal, which is either helping the crystal growth to grow into a good quality, or if you change the parameters, sometimes defects generation starts. So we set up this optical techniques, which is nothing but a small laser. We use a helium neon laser of low power, something like 5 to 10 milliwatt. Then we have a special filter. Special filter is nothing but a beam expander and a collimator and a pinhole arrangement, which basically removes the defects in the beam. It basically makes the beam very smooth, right? And then this parallel beam of light is made to pass through a chamber. Now these chambers are specially designed. I'll show you the photograph of the chambers. These are specially designed because you have to have flat windows on both the ends, because the laser has to pass through it. If there is a curvature, then these two ends will behave as lenses, and which we do not want. We don't want the ends of the crystal growth chamber to behave as lenses. We want the beam should fall on flat faces, and inside the crystal is growing. So whatever image you see on the screen is actually the information of the concentration as well as the flow fields inside the crystallizer. And the images will show you what beautiful images we were able to see. And finally, we have, of course, this signal acquisition and data processing instrumentation. We have CCD camera or a video camera in which we continuously record the experimental images, and then there is a video monitor, a frame grabber card, and image processing software, and finally a PC. And this is the governing equation which governs the process of shadowgraphy when it is recorded in this geometry. IS is the image intensity on the screen when the disturbance is present in the beam path. I naught is the intensity when there is no crystal growth happening, that is, there is no disturbance in the beam path. L is the length of the chamber, right, through which the beam is passing. D is the distance between the exit end of the chamber and up to the screen, right? And this NXY is basically the refractive index along X and Y direction, and along Z direction the beam is propagating, right? And this is log N of NXY field, and this curly square by curly X square plus curly square by curly del square. This is basically the double differential of this log N field, right? So this is the equation which we have to solve. This equation is derived with a very simple mathematics which can be followed, and this is what we see during experiments. So laser shadowgraphy has been used for imaging fluid dynamics and quantifying its strength in terms of Grashof number and finding a relationship with the crystal quality. So what we do is, this is a seed crystal when the crystal has been put inside the chamber. This is how supercooling is because once we are growing with solution growth, we have to cool the temperature. So when you are cooling it, the crystal will start to increase in dimension. And this, what you see is the increasing dimension of the crystal. And if you see closely, you will see two black lines which are emanating from the top surface of the crystal. These two lines are nothing but the undersaturated solution, because the solute has got deposited on the crystal surface, and that solution which is adhering to the sides or edges of the crystal is now undersaturated, and because of the effect of buoyancy, this undersaturated solution will start to rise up, and this undersaturated solution is of different refractive index as compared to the refractive index of the solution surrounding it. So the beam which is passing through the parallel beam of light get deflected, and because of which the contrast of the region which otherwise was having a uniform intensity, that contrast changes, and you will see these black streaks which are nothing but the light from these regions have got deflected to the other region, and here we are seeing black region. So, and these are called, in fluid dynamic language, these are called plumes, and these plumes are what we record. And the fluid dynamic behavior of these plumes, whether the plumes are laminar and stable, whether they are irregular and stable, or they are chaotic, the behavior of these plumes give us the information whether the crystal which is growing inside will be growing with good quality or whether it will pick up some defects. If the plume dynamics is such that they are chaotic, that is the stage when the crystal picks up a lot of inclusions. So we have to ensure, we have to optimize the growth parameters in such a way, in online manner, that we don't go to that condition wherein the plume behavior becomes chaotic. We want to work in the region which we refer to as laminar and stable region, in which whenever the crystal is growing with laminar and stable plume behavior, the crystal grows with absolutely nice quality. So this was as far as the qualitative discussion was concerned. So we thought that why should not we quantify this? So then we thought, okay, again we took the cue from fluid dynamic literature, which refers to Grashof number. Grashof number is a fluid dimensionless number which characterizes the strength of free convection in a fluid dominated process. Crystal growth from solution is a fluid dominated process, and we calculated the Grashof number at all these 5 stages of these are 2 different experiments. In one experiment, the crystal has been put on top of a capillary tube, right? And crystal is growing. In the other experiment, you will see that the crystal has been put on a platform and the crystal is growing in size, right? So these are 2 different experiments which have been done, in which one crystal is hanging on top of a capillary tube, and in the other, the crystal is grown on a platform. The rapid growth technology of Professor Zaitseva of Lawrence Livermore, that experiment was simulated here, and we were able to calculate Grashof numbers for both these experiments, and what we found was this is for crystal on top of a glass rod or a capillary, and this is crystal grown on a platform. We were seeing that suddenly there is a jump in the Grashof number, and this range of Grashof number, which we say is the critical Grashof number, beyond this Grashof number, we were always seeing that the plume behavior is chaotic and the crystal is picking up intrusions. So this was something which we concluded, and we were able to show that there is a relationship between the cooling rates and the crystal quality and the plume behavior which we were able to record. Right. So this is how we found out. Now, next I'll show a similar type of experiment, but for some other application. This is a zinc thiosulfate. As I told you, we have worked extensively on zinc ZTS crystal for its nonlinear optical applications, and also computationally found out its morphology using Hartmann per-Dog theory. Those of you who have done computational work on crystal morphology, they would know that Professor Benema in Netherlands, he has spearheaded a very extensive program on computational determination of crystal morphologies using Hartmann per-Dog theory. It is also referred to as periodic bond chain theory. So we also used long back, 15-20 years back, that theory, and we were the first to find out computationally the ZTS morphology. And then we also confirmed whatever computations we have done by whatever programs we had written at that time, codes which we had written, which we run and obtained the computational morphology. We did experiments to find out, and we were able to show that whatever morphology comes computationally, the same morphology we get experimentally. Now, this work which I am showing this came little later after those works, because again, this work was done as part of the PhD work of Dr. S. Dinakaran. I instructed him that why not, because those two works which I was talking about, computational work and the experimental work, computational was purely computational and experimental was purely experimental. There was no connection between them. But I told him that let us do an online in situ imaging of our growth experiment, and we wanted to find out why this crystal grows in a polar morphology. ZTS belong to a polar space group, PC2A1, right? So it's a polar group, and the polar group is oriented along 0, 1, 0 direction. And you will see that this crystal is growing. On the left hand side, if you see these images, you will see that this is the glass rod on which this crystal is growing, right? And this basically I would say a half cut hexagon type of thing is the crystal which is growing, and this time which you see 0 hour, 105 hour, 120 hours, 191 hours, this is the duration of the experiment. So you can see that this experiment continued for more than 10-15 days, and continuously. This is the video camera which I was talking. This is a Sony Handycam which was continuously recording this experiment, and we used to record these cassettes of this experiment, and then we used to run these cassettes on our PC and then take out these images at corresponding hours, right? And we did two different experiments. So in which one we mounted our crystal in plus 0, 0, 0, 1, 0 direction, and in other we mounted the crystal in 0, minus 1, 0 direction. And we were able to tell that why this crystal grows in a polar morphology, why there are more number of phases on plus C side and less number of phases on the minus C sides. And this was the strong anisotropy in the growth rate along 001 and 00-1 directions, leading to polar morphology was found due to different bonding arrangements of the two sides of 001 layer. So we found out what was the bonding arrangement in a 001 slice of ZTS, and we were able to show that there are certain bonds which are present only in 001 side, but they are not present on the 00-1 side. And those dangling bonds are the reason that most of the growth units are coming and attaching to that surface, and nothing is going on the other surface, because of which excuse me, because of which the crystal was growing more in one direction and less in the other direction. Excuse me, I'll just take some water. . Yeah. So we were able to sort of find out how and why there is a change in the morphology of this crystal using shadowgraphy. And we computed online manner the growth rates, and these are the growth rate curves on the bottom left and right side of this. And now this is again in KDP crystal we did experiments to find out what happens when we grow this crystal under different conditions of supersaturation. When we are growing this crystal under low supersaturation conditions, we were able to see that the crystal is growing only along one dimension, right? So basically only it was elongated along X and Y direction only. There was no fattening of the crystal taking place. And that was clear from the plumes which were visible from the edges of the crystal. You can see these plumes, small black lines which are emanating from this edges of the crystal, and these black lines are because the crystal is growing mainly along this direction and this direction. So this we called as edge plumes in shadowgraphy images, and this is the representative of one-dimensional growth mechanism. Here crystal grows along only one direction, and this mechanism is operative at low supersaturations. Then when we increase the supersaturation, we were able to see that the plumes which were earlier emanating only from the edges of the crystal, now we were able to see that the entire surface of the crystal was getting, and the plume was rising from the entire surface of the crystal. And this is which we refer to as the 2D growth mechanism. And here crystal grows layer by layer. This mechanism is operative at moderate levels of supersaturation. And finally, we did another experiment in which we increased the supersaturation very fast. And what happened in that case was we were able to see that the plumes which were initially visible only from the edges of the crystal, and in the second case from the entire surface, but only an envelope of the plume was increasing. In the third case, we were able to see that there were multiple sources of plumes on the top surface, and this shows that now the crystal is growing at several locations, and this was the case of 3D growth mechanism, or in literature it has been referred to as birth and spread type of growth mechanism. Here crystal grows with very high growth rate along all the three dimensions. So this is how we have been able to show that shadowgraphy can be used for in situ online imaging of the growth process. Now let me go to the next technique, which is Mach-Zehnder interferometry. This interferometry has been used for quantifying the concentration gradient about diffusion boundary layer or solutal boundary layer around a growing crystal, and also we have optimized the forced convection convection parameters during growth of the crystal. These are some of the reference interferograms which have been captured using this interferometer. I'll not go into the details of the alignment of this interferometer. This interferometer basically can be aligned in wedge and infinite setting, and we performed experiment in both these settings, and the reason when we use wedge and when we use infinite setting are different. So let me just skip that part, because otherwise we will be because of the less time available, I would like to just go to the crystal growth, what we have done. So you see, these are some of the Mach-Zehnder interferograms which have been captured online online in an in situ manner, right? So what we do is this is the setup. Basically, you have this Mach-Zehnder interferometer in which there is a growth chamber, and in the other there is a compensation chamber. So we are making our crystal grow in this chamber, and in the other chamber there is only solution. There is no crystal which is growing, right? So when the beam is passing through this, right, and these two beams interfere, you will get an interferogram. Now when a crystal is growing, right, so the solution around that crystal, the diffractive index of that solution will continue to change, and because the light beam is sensitive to changes in the refractive index, you will see the changes in the fringe pattern, and that fringe pattern is then correlated with the growth parameters, and finally with the refractive index of the solution from which the crystal is growing. And then we correlate what were the changes which were occurring in the solution during the growth, which have resulted in either the good quality of the crystal or bad quality of the crystal. If the crystal grown under certain conditions are bad, then we online itself, when the crystal is growing, these are the images which we see directly always on the image. So if a crystal is growing for 30 days, we see whatever is happening inside the chamber on an image, on a screen continuously. So whenever we see that the crystal is picking up inclusion, we immediately go and change the temperature profile. We either increase the cooling rate or decrease the cooling rate, or for some time, maybe a few hours, we make the temperature constant so that there is no growth. And in fact, when there is an inclusion, we try to dissolve the crystal slightly. Right? So we increase the temperature so that the solution near to the growing crystal becomes under saturation, and that region where the inclusion has picked up, that gets dissolved, and then we give a small cooling. So these types of online feedback mechanism, this optical techniques have provided us, and that is how we have been able to tailor make our growth process and optimize our growth conditions so that we get good quality, large size crystals required for our programs. Right? And on the right hand side, you see there is another result which is optimizing force convection parameters during growth by Alexander interferometry. What we did was we performed an experiment in which KDP crystal was growing and it was continuously rotating, because when we are growing a crystal in from solution, it is also rotated because we want to homogenize the solution from which it is growing. So in that case, basically we are adopting forced convection regime. And in literature, if you read, literature refers to a technique of achieving forced convection, which we call as accelerated crucible rotation technique. That technique is actually used for Czochralski growth of system, in which a crucible or the crystal which is growing, that seed rod and the seed, that is actually rotated in a clockwise manner, and it slowly starts from 0 and it increases in RPM, and then it becomes constant, and then it goes down and it stops. It stops for a few seconds, right? So you will see in the clockwise this sinusoidal type, not sinusoidal, this wave which you will see that there is an increase in RPM, then there's a constant RPM, then decrease in RPM, and then 0 RPM. So this 0 phase is the stationary phase, and then the crystal starts to rotate in opposite direction, anti-clockwise direction, and this is the one cycle of ACRT. So we followed this mechanism of forced rotation, and then using our interferometric techniques, we were able to find out what should be the values of times for which it should be accelerated, it should be constant, then it should be decelerated, and then it should be stopped. And what we did was we mapped the concentration fields continuously during the different parameters of our experiment, and we were able to show that what are the optimized values of these T up, time steady, time down, time stationary, and also the rotation rate. What RPMs should we use so that we get uniform concentration field around the growing crystal, because that is what is desired. That is what will give us a uniform growth rate and also good quality crystal. So we have optimized these post-convection parameters by using these interferometric techniques, and all these works have been published in very good journals. And then, okay, this was one more very interesting work which was done again by one of Dr. Senthil Pandian, who is now in SSN College. I think everybody who grows crystal knows, because we regularly get emails, updates from him on whatever is happening on the crystal growth front in India, because he is now some sort of, you can say, a repository type of person, a resource person who keeps on informing us about whatever is happening. So he was working with me long back when he was doing his PhD. Professor Ramasamy wanted to know what is the reason that we are able to grow these crystals, solution growth crystals in SR method. So he wanted, when he saw our results on this shadowgraphy and Alexander interferometry and all, so he said, can we do some similar experiments in our SR growth system also, and can we find out whether in our SR growth system also, what is the reason that we are able to grow these crystals? Because in case of large dimension solution growth crystals, we were able to do those imaging experiments. But then he asked me, can we model some experiments so that we can get these results. So I told him, okay, we will devise a model experiment. So in which we made this apparatus, because usually the SR growth systems require a circular ampule, right? We have a cylindrical ampule which is put inside the growth chamber. But we can't use a cylindrical ampule for imaging, because once we put a laser beam, expanded laser beam through a cylindrical ampule, it will focus the beam because it's a curved surface, right? So we have to make a model system, a model apparatus in which the side faces through which the beam will pass through should be flat. So instead of a cylindrical ampule, what we devised was we made a square ampule, right? So you see on the left hand side, this is one of the sides of that square ampule, and this is the side figure, and this is the top figure. So this is the chamber which we filled with thermostated water, and this was the inside chamber, which was basically a square not cylindrical, a square long tube, right, in which the crystal was growing. And this is the seed crystal. This is a benzophenone crystal, 100 seed crystal. This was of 1 inch by 1 inch dimension, and this cell was also 1 inch by 1 inch, but 7 inches long. 1 inch by 1 inch X and Y, and Z was 7 inches. So we put the seed crystal at the bottom of this, then we filled up this with a solution, and these are the results which we sort of obtained using our shadowgraphy, Maxenter interferometry, and we were very comprehensively able to show, and what Professor Ramaswamy wanted actually, that what is the reason that a crystal is growing, because there were a lot of questions which were coming on SR growth technique, that what is the reason, please tell us the reason that why this crystal is growing in this way when whole of the world is growing the crystal in large chambers, and you are growing this crystal in small ampules. But the quality of the crystal was very good, but the crystal dimensions were good, and in fact the conversion rate from solute to crystal was also 100%. So SR growth had all positives, right? So they wanted to do some basic investigations and find out what is the reason. In these imaging experiments which we performed, we were able to for the first time show that it is the gravity driven concentration gradient which is set up inside the crystallizer, inside those ampules, which is actually allowing us to grow the crystal. So, and this work has been published in very good journal, and it has received very well by the international experts. So we were the first to show that in SR growth how a crystal is growing using convection and gravity-driven convection gradients, and also the concentration gradients. Now, there is another technique which we call as birefringence interferometry. This technique is used for real-time and in situ studies of growth kinetics. What we do is, if your crystal is birefringent in nature, so what we can do is we can use that birefringent nature to grow a crystal and measure its growth rate in different directions, especially in the direction of birefringence. So the principle is something like this. You have a helium neon laser, you polarize it, and you expand it. Now this polarized laser, when it passes through a crystal which is birefringent along a particular direction, it will split into extraordinary and ordinary ray. And then these extraordinary ordinary ray, when they pass through analyzer, so initially we align the setup in such a way that the polarizer and analyzer are crossed to each other. So at the output, we will not see any output beam, right? Now you put the crystal inside the growth chamber. Because the crystal is birefringent in nature, some of the plane of polarization of the incident light will change, and then some of the light will be able to pass through the analyzer, and the component of the E and O, which is along the axis of the analyzer, will interfere, and it will produce an interference pattern. And this interference pattern will continue to change as the crystal grows, and depending upon how many number of fringes have passed the field of view, you can find out the growth rate of that crystal along that direction. And we have been able to use this technique to find the effect of temperature as well as pH on the KDP crystal growth morphology, and we published it long back. So this is a technique which we now very regularly use on many different crystals. This is a Michelson interferometer which we have set up, which we use for investigating, which we use for basically finding out what is the growth mechanism, especially if the growth mechanism is a screw dislocation mediated growth mechanism, then we can find out that using this Magenta interferometry. What we do in this technique is you have an helium neon laser, you have a beam expander, you have a beam splitter, so half of the beam will go this way and half of the beam will get reflected. And this is the chamber where the crystal is growing. So in this crystal, in this chamber, you have the surface of the crystal which is growing, so we will make the beam get reflected from the surface of the crystal which is growing, and these two beams, the reference beam which is reflected from the mirror and the test beam which is reflected from the crystal surface, they will come and interfere, and the CCD camera will record these interferograms. And these interferograms, you will see that these are having concentric fringes, right? This circular type of fringes are there, or some irregular circles are also there. These are nothing but these are the fringes which are recorded from the hill. The dislocation mediated growth, what will happen is there is a dislocation and there is a screw dislocation, or spiral growth mechanism the crystal is growing with spiral growth mechanism. And what will happen is there will be a hill formed. A hill will be of a micron dimensions, and that hill will be formed, and when a laser beam is falling on it and getting reflected from that surface, so you can, Newton's rings types of fringes will be formed. It is something similar to that, right? So, and these are how we were able to record movement of dislocation hillocks on 101 facet of KDP with saturation. And similarly, we were able to, if there are multiple sources of dislocations, we were able to see the competition between dislocations of different strength over 100 facet of KDP. And we also were able to quantify what was the normal growth rate, what was the slope of the hillock which was generated by the screw dislocation, and what is the tangential velocity of the steps which were created by that screw dislocation. So in this way, we were able to quantify what was happening on the surface of the growing crystal in a very, very microscopic manner. Now, this is one more work which one of my students did long back, which is basically use of double or maybe multiple interferometric techniques. So what happens is usually we use one lambda to image our experimental process. But what happens is sometimes there are two competing parameters in a growth process. For example, we all know that in case of solution growth, the temperature as well as the concentration. So these are two coupled fields, right? Temperature as well as concentration. Both of these fields depend on each other. If you increase the temperature, concentration decreases. If you decrease the temperature, concentration increases. So these are inversely related and they are coupled. But usually we neglect the effect of this temperature, because we say that we have reduced the temperature either 1 or 2 degrees, and whatever is happening is only because of the concentration fields. But we thought that we should be able to use some technique so that we can delineate the temperature effect from the concentration effect. So we used a technique which we refer to as dual wavelength or multiple wavelength interferometric imaging. In this, what we do is we will record the growth process online and in situ manner at different wavelengths. One of the wavelength is sensitive to temperature changes, and another wavelength is sensitive to concentration changes. And then using these two wavelengths, we were, in case of this experiment was done for triglycine sulfate, and for triglycine sulfate, we were able to find out what was the measured thermal driving force and what was the actual thermal driving force. In case of experiment, we were able to show what was the contribution from thermal effects and what was the contribution from the concentration effects. So these advanced techniques also which we have used for solution growth, for understanding the basics of solution growth. And this is a very advanced technique which we refer to as three-dimensional imaging of convection features using computed tomography. You all know that when a crystal is growing, everything is three-dimensional, right? It's a three-dimensional object which is growing inside the three-dimensional chamber. But when we are recording it in the form of images, image is nothing but a two-dimensional representation of a process which is actually three-dimensional, right? So you all know we go for CT scans, right? So CT scan is nothing but computerized tomographic scan. So we record several multiple images from different angles, and then we stitch them using some computer algorithms to get the complete information about, depth-wise information about our brain. So we use the same algorithms. We devised a growth chamber in which you can see this growth chamber. this growth chamber was having 8 windows, right? So earlier growth chamber which I showed was only 2 window. This is the 8 window chamber, right? So we were able to record the growing crystal convection fields from multiple directions, and then we use, these are the images which we recorded from multiple directions, right? You can see this is the crystal, and then slowly and slowly the chamber was rotated, and then it became 90-degree. So this end of this crystal from this side looks like this, and then again it was after 180-degree it looked like this. So this left side becomes right side, and this, right? So you can see that these are rotated by 180-degree, and in between at every 10-degree step we have recorded the shadowgraph images, and these shadowgraph images were then used using 2 different computer algorithms, which we refer to as convolution back projection and algebraic reconstruction techniques, to find out what is the 3-dimensional pattern of the convective fields and also of the convection or the concentration fields on the surface of the growing crystal at different heights of the crystal. And we were able to show from there how the convective fields are spreading from the top of the surface when the plume is rising, and how it is getting disappear in the bulk of the solution. So we were able to reconstruct these convection and concentration fields at different height, 0.25h, 5h, and 75h is basically total height we take as h, and then 75% of that, 50% of that, and 25% of that. And these were the results which we showed for KDP. And now this is what I was talking, multimodal optical imaging incorporating shadowgraphy, interferometry, and tomography. What we have done is, initially we set up these experiments separately, but then now we have made a complex setup in which either we remove one of the component or 2 or 3 components, and it behaves as a shadowgraphy setup. If we put some components that behave like Eschleren or double Mach-Zehnder interferometer, so we can do simultaneous recording of Mach-Zehnder, shadowgraphy, and double shadowgraphy and computerized tomography in the same setup using these integrated multimodal optical imaging setup for our basic research studies. Now finally, I come to the last part of the lecture, that is the defect characterization. I'll try to go through fast because I think I have taken time more than what I was allotted. I'll just take 10-15 minutes more, and I'll try to wind up. So I think some of the techniques which are very standard, I'll just cover in a very fast manner. So this one of the very conventional ways in which all crystal growers will first test their grown crystal is UV visible and IR spectroscopy, right? So what we do is, we, for example, in case of lithium niobate, once we had doped it with iron, we try to see what is the transmission. And you will see that before annealing, after annealing, so we were studying the influence of annealing of this lithium, acid-doped lithium niobate, and we were able to find out that there is a drastic change in the transmission of this. Also, there were certain defects which were getting annealed during the annealing process, and this was one of the interesting studies. Similarly, in case of KDP crystal, we have cut different plates, 100 plate, 010 plate, 101 plate, and 001 plates, right? So these are 4 different directions of KDP, and we cut plates parallel to that, and then we wanted to investigate how this, what is the transmission at 1064, what is the transmission when the frequency is converted to 532, so second harmonic generation, then third harmonic generation 365, and fourth harmonic generation 266. So we did these transmission studies on KDP, different plates of KDP, different samples of KDP, and we were able to show that transmission at different wavelengths of interest, basically first fundamentals, like first harmonic, second harmonic, third harmonic, what is the value. And this not only showed what is the transmission at different wavelengths of interest for device applications, but we were also, this is a 10 centimeter by 10 centimeter by 10 centimeter crystal, which was grown, right, and by my colleague, and I did the optical and the X-ray topographic and other defects characterization and correlation with the optical properties. So in this, you see that this big sample, which is 10 centimeter by 10 centimeter, absolutely clear sample, we made multiple UV visible and IR spectroscopy measurements, and we were able to show what is the spatial variation along the direction of this crystal, right? In the transmission of 1064, 532, 355 and 266, right? So we were able to record such types of images. Now this is the earlier Mach-Zehnder interferogram which I showed you was used for in situ and online monitoring of the growth process. The same interferometer, if you are not having the growth chamber in the beam path, you can use it for ex situ quality assessment of your grown crystal. You put the crystal sample, which is in the form of a plate, in the beam path, and you will see interferograms like this. So Mach-Zehnder interferogram in infinite fringe setting mode looks like this. This is for lithium tetraborate sample, and you will see that these straight and parallel lines show that the crystal is free of defects, major defects. And here you will see that although the fringes are parallel and straight, but they are not equispaced. And this is because there is a curvature in the sample after getting it polished. So that curvature is showing these types of artifacts in the fringes. And these are Mach-Zehnder interferograms for KDP crystal with 100 plate, 001 plate, and 001 top and bottom plates, right? So you will see that here there is a defect. You can see that there is a distortion in the fringes here, and the circular fringes pattern is coming because there is a curvature. After polishing, there is a mild curvature in the sample. And these two, A and C, basically they show equispaced parallel lines which are representative of very good quality sample. This is again birefringence interferometry. Birefringence interferometry, basically conoscopy, which we usually do with optical microscopy, is also a form of birefringence interferometry, because you all know when you have a focused beam of white light or maybe a laser light, that beam, when it is made to pass through a crystal sample, then because it is not passing through the optic axis, the lines, because they are forming an angle with the optic axis, they will split into E and O ray, and through the analyzer some component of the beam will be able to pass through, and then they will interfere and they will produce these concentric fringes, and these maratopes and iso bars will be formed. These are the images which have been formed using helium neon laser, so you see only one color. These are the images, conoscopic images, which have been formed using white light. So you see a different color, complete spectrum, wave by B, G by OR in each of these fringes. So for different wavelength, they're different, for different thickness of the crystal, different wavelength is coming in constructive and destructive fringes. So we get different color in the same interferogram, right? So, and these work have been done on ZTS crystal. This work has been done on KDP crystal. And we regularly use laser-induced damage threshold setup also for investigating what is the damage threshold value for our grown crystal. And laser damage threshold value is defined as the lowest laser intensity at which mechanical damage occurs on the sample surface or in the bulk. LDT is an important property of optical material for deciding its application for high power laser applications. The mechanism for the laser induced damage in crystals are thermal breakdown, absorption of impurities, self-focusing avalanche ionization, and multiphoton absorptions. And there are various ways in which these LDT values can be measured, and for these are referred to as one shot per site or n shot per site or multiple shots per site. I'll not go into the explicit details of this. This is a very regular, usual technique which is found in literature, and this we have, which we use regularly. And these are some of the results of LDT which have been found, which we have used for KDP crystal, and lab crystal is another nonlinear optical crystal, and these are some of the experiments which we did. Similarly, we have second harmonic generation experiment in our laboratory, in our division, which was used for some of the experiments for finding out the efficiency of some of the crystals which we have grown. And a high power laser is used, which is a Q-Assist ND-ARC laser of 1064 nanometer operating in TEM00 mode with pulse repetition rate of 10 Hz and pulse width of 6 and 8 nanoseconds with beam diameter of 9.5 mm. The procedure is that first the beam is focused using a lens on the specimen in single crystal or powder form. You can do powder SHG or you can do single crystal SHG, which is mounted on a goniometer, which is having XYZ and R theta phi sort of degrees of freedom to align the sample in the phase matching direction. Then the SHG output from the specimen passes through an IR cutoff filter where the fundamental component is filtered out and only the SHG signal gets transmitted. The SHG output is sent to a monochromator and then amplified by a PMT. The output from PMT is fed to a digital oscilloscope. You see here, to get the relative SHG efficiency with respect to a standard NLO crystal under the same experimental conditions at that of the specimen. The output of the oscilloscope is acquired by a camera or further computer for further analysis and processing. So this is how we usually, this is a complete setup which you are seeing, and this is the procedure which we use for measuring the second harmonic generation. And I told that lithium niobate is a very good optical data storage application, and two-wave coupling experiment is what we do to find out its data storage properties. So here what we do is we make one beam split into two beams, and these two beams are then made to interfere inside the crystal. For example, what you see here, this beam 1 and beam 2 are coming and they are interfering inside this. And because it is a photorefractive material, photorefractive means you can change the refractive index of the material using photons, right? So lithium niobate is a photorefractive material. So when the light beams fall on this material and they interfere, so what will happen is the fringes will be formed. And at the position of the bright fringe, the electrons will get, electron will migrate from there. Electrons will get migrated and they will move toward darker fringe, and after some time you will see that the refractive index modulation have been generated inside the crystal, and those modulation are of the form, they will follow the refractive index they will follow the fringe pattern which has been formed inside this crystal, right? So in this way, then once this refractive index profile has been formed, this refractive index profile behaves like a Bragg's grating, and it starts to diffract the same beam which has formed these two this refractive index profile inside the crystal. And this process of formation of the refractive index grating and diffraction of that grating and then erasure of that grating is what we record. So you will see there are three parameters which we measure from these experiments. One is called diffraction efficiency, another is called recording time, and third one is called erasure time. So these three are the main parameters which we have to sort of characterize for any material which we sort of think of that it can be a good optical data storage material. So in case of lithium niobate, we have done these experiments using two-wave coupling, and we have been able to find this material for iron doped lithium niobate and also iron and manganese doped lithium niobate. And we have been able to show that iron and manganese doped double doped lithium niobate is a better material as compared to single doped material. Z-scan is another one of the technique which we use for finding out the nonlinear refractive index and nonlinear absorption of NLO materials, and this is the setup which we have used, and we use this for closed aperture Z-scan and open aperture Z-scan. Closed aperture Z-scan gives us the N2 value, which is the nonlinear refractive index, and open aperture Z-scan gives us beta value, which is the nonlinear absorption coefficient. And by finding out these nonlinear refractive index and nonlinear absorption values, we can find out the third order nonlinear susceptibility through this formula, which have only experimental values are N2 and beta, all other values are constants. And for benzophenone, we have recorded it for multiple crystals, and I'm just showing one of the sample which we used, and these are the values for benzophenone crystal using Z-scan. Now, as far as the defects are concerned, we all know who grow crystal that there are different types of defects in a crystal. And these defects sometimes are detrimental and sometimes they are deliberately required. But most of the time they are not desired, especially for device applications. So what we have set up in our lab is a very sophisticated X-ray diffraction topography for imaging defects in crystal. This is a very specialized optical X-ray instrument which we have in our lab, which we call as a digital X-ray topography instrument. And these are some of the crystals for which we have been able to generate the X-ray topographs, which give us the what is there inside the crystal. A crystal may be this, for example, these three samples. You can see that the samples are appearing absolutely perfectly fine. They are completely transparent. But when you subject them to X-ray topography, you see the seed edges, you see striations, you see misoriented regions, you see these dislocations, you see these inclusions inside, or otherwise you are not able to see anything. So what we have done is, whatever crystal we grow, we subject them to not only the optical investigation, the one which I have shown, X-ray, UV visible, then Alexander interferometry, then basically Bareffin's interferometry, right? We also subject them to peep inside, deep inside the crystal, what are the lattice distortion, what are the defects, what are the inclusions, where are the more inclusions are more, where the inclusions are less, where there are misoriented regions of those lattice planes for which we really want a device element to be fabricated. You see, in case of KDB crystal, this crystal was appearing absolutely transparent. UV visible transmission was absolutely perfect, right? 80-90%. But once we did X-ray topography, we were able to see there is a huge dislocation near to the seed crystal. And this is what is reported in literature also, that when you grow a crystal, the initial defects start generating from the seed crystal, but you as go away from the seed crystals, the crystal quality becomes better and better. And we were able to show from these X-ray topographic experiments that where from one should be able to cutting the crystal for device application, where one should avoid it, right? So these types of investigations we have done. We have also done HRXRD. I think it's a very common technique, high resolution XRD, in which we record the rocking curves, right? We will mount our crystal, we will rock it along it, we will decide about a particular reflection, for example, 400 shown here, and then we will mount it along, we will be fixing our detector along 2 theta corresponding to 400, and then we will rock that crystal slightly along 400, and if the rocking curve is very sharp, then we say that the crystal quality is good because there are no mosaic defects. If the rocking curve is very broad, then we say that the crystal is having some crystalline imperfections, right? So this is used to find out the crystallinity, how good the planes are oriented. Are there any mosaicity? Are there any dislocations or curvatures which are resulting in the broadness of this dislocation, this rocking curve, right? So we have been able to record these for many of our materials. And then we also use our synchrotron source. I told you Indus 1 and Indus 2 are two national facilities which are being offered to all the students throughout our country. And we have also used it extensively for many of our studies. And I'm just showing one of that study, which is for finding out the metallic impurity distributions in our crystals, right? So we use X-ray fluorescence for that. So I'm not going to elaborate on the principle of X-ray fluorescence. I think most of us will be knowing what is an X-ray fluorescence is. So what we do here is we mount our crystal in the beam path, which is a beam line. In case of synchrotron radiation, a large beam line, large infrastructure, and that beam line, once that X-ray falls on it, the X-ray fluorescence is captured by a detector, and that fluorescence is basically a fingerprint of what all elements are present in your sample. So because we know that our KDP crystal is having potassium, KH2PO4, so we know K peak corresponding to K will be there, peak corresponding to other similar elements in that will be there, but we were able to find peaks corresponding to Fe and also to some extent aluminium, and these were the impurities which we were looking at, right? So we were able to quantify the metallic impurities present in our KDP crystals using our X-ray fluorescence, using Indus 2 synchrotron radiation source in RRCAT. And LTP crystal, I told you, it's a very good dosimetry material. We have been able to, dosimetry is usually offline dosimetry is characterized using thermoluminescence dosimeters. So we have thermoluminescence dosimeter in our lab. We grow this crystal, we irradiate this crystal using our gamma sources which are present in RRCAT, and that gamma, once basically you have irradiated your sample using gamma rays, then you put that irradiated sample in the thermoluminescence dosimeter reading system, and it will heat the sample. Because it is thermoluminescence, once you heat it, it will release some amount of radiation, luminescence. That luminescence is recorded, and that luminescence is characteristic of what amount of dose was given to that particular sample. And this material is used for personal dosimetry. So whosoever is going in the radiation environment, he will wear a badge which we call as TLD badge, thermoluminescent device, and that device will record the amount of radiation which that radiation worker has received, and after receiving, that badge is then read through a thermoluminescent dosimeter, and we record these glow curves, and these glow curves are characteristic of how much, what is the area under the curve will tell you what is the amount of radiation that particular worker has received, because every radiation worker is monitored very closely, because there is an annual dose limit to which a radiation worker can be subjected to. So if the annual dose limit of a particular worker has been reached, so he will be immediately taken out of that radiation environment, and then for the subsequent part of the year he will be assigned some other duties. He cannot be assigned the duties which are basically for the radiation workers. So this is how these types of batches are used based on our lithium tetraborate samples. So I think this was all which I wanted to describe, and I have reached at the end of my talk, and here I will take just a couple of minutes. I thank the management, the Father Secretary, Father Rector, and all the students, faculty of Loyola College for inviting me to this special lecture in honor of Professor S. Jerome Das. And thank you for your time and patience. And I especially would like to acknowledge Professor S. Jerome Das for about 2 decades of scientific association and personal friendship, and all the management and staff and faculty and students of Loyola College for instituting an endowment lecture in his honor. And several colleagues at RRCAT have worked very closely with me, and the seniors also at junior level also. Dr. Bartwal was one of my seniors whom I had the privilege of working, and I acknowledge him, although he is not, he's retired now, but my reverence is to him also. And there are, in fact, Dr. Majumdar is the new head, and I'm receiving a lot of encouragement for all these studies. And of course, my director, Dr. S.V. Nake, who is supporting me and encouraging me to conduct all these investigations and many more. And there are collaborators with whom I have been working for almost more than 2 decades now, Professor P. Ramaswamy, Dr. M. Senthil Pandian, Dr. Bhagwanarayana, Dr. N. Vijayan at NPL. Dr. Bhagwanarayana was also at NPL, now he's retired, he's now somewhere director in some other institute in Andhra Pradesh. And of course, P. Ramaswamy continues to guide many generations of crystal growers. And I see Professor Jerome Das going along the same way, because I see 33 of his students have already passed out, and I'm sure soon we will be hitting the number of 50 PhD students in a couple of years from now. And I would be very, very delighted to see that day come soon. Right? And there are many students of Professor Jerome Das who have worked with me, either worked with me or I had the privilege of sort of having discussions with them, scientific discussions whenever I used to visit Loyola College. For example, Dr. Justin Raj, Dr. S. Krishnan, Dr. S. Dinakaran, Dr. K. Raja, Dr. Alvin, and many more. So I thank all of them. And now I think I'll stop here. I'll hand over the mic back to you. Thank you very much. So,
your presence and voice will help signify. Wishing you all the best for your future endeavors. It is now my pleasure to welcome Dr. S. Jerome Das, Head Department of Physics, Loyola College, to deliver his message.
Good evening, Honorable President. The flags are flying, balloons are ready for release. Yes, it's a great day in my life, the one we have been planning and waiting for. I extend my immense gratitude to most respected Reverend Dr. Francis P. Xavier S.J., Founder Director of Life, Founder Director of Loyola Engineering College, and currently Vice President of Loyola Institutions. A man of humbleness, stands as an indigenous inspiration, directors from utility to user and from non-materials to new products of social and societal concern. Thank you for your continuous motivation day on Father. I thank Reverend Father Secretary, Reverend Father Principal, and former Reverend Father Secretaries, Reverend Father Principals for their strenuous system services rendered to me during my service span in Loyola College. I thank my parents from heaven watching the entire proceedings with a deep respect. I recall thankfully support by Reverend Father Leo Korea SJ and Reverend Father Joseph Njeka SJ. The management of Loyola College motivates us to analyze our strength, weakness, opportunity, and thrives for the development of lab-to-land applications, having multiple plans, better strategies to effectively confront the cumulative challenges combined with the global competition. Thank you, dear fathers, and each one of the members of Loyola management. I wholeheartedly thank the speaker, Dr. Sunil Verma, an eminent scientist, a man of simplicity, erudite scholar, come scientist, sincere in every aspect of job he undertakes, for accepting our invitation and taking out his pleasurable time, and for having made this first endowment series a remarkable, dynamic, and memorable one. Thank you, dear sir. I thank Dr. J. Madhavan, Dean Research, Dr. J. Marian Shela, Director Life, Dr. P. Savaraj, for their continued support in all my endeavors. I thank their teaching, non-teaching staff members of Department of Physics, who are the frontline workers, for your valuable presence, amalgamated attempts, and support. Experience is not what happens to us, it is what we do with what happens to us. The tireless effort carried out in our research lab for the past 35 years has borne 34 fruits and featured doctors who are all well placed in different institutions worldwide, having numerous publications to their credit, which reminds me of this most fitting Thirukkural number 68. 6 plus 8 is 14. தம்மின் தம்மக்கள் அறிவுடைமை மாநிலத்து மன்னுயிர்க்கெல்லாம் இனிது. தம்மின் தம்மக்கள் அறிவுடைமை மாநிலத்து மன்னுயிர்க்கெல்லாம் இனிது. I warmly extend my heartfelt thanks to all my doctoral candidates of Department of Physics for their cogent contribution, convoluted collaboration, and involved initiatives for the successful conduct of this first endowment lecture series. I thank my current research scholars for their potent assistance towards the success of this great event. I am sure the younger generation of scientists, technologists, industrialists who are our real hope will place the emerging world in rightful position. I am doubly sure that public understanding of science needs to be matured by scientists' understanding of the public. I am doubly sure the public understanding of science needs to be matured by scientists' understanding of the public, and the valuable endowment lecture delivered by Dr. Sunil Verma is a step ahead in that direction. I am sure I have taken a little bit of time to thank all those who are present, who are with me throughout my journey in this college, not only in this college, but also outside this great institution. I am extremely thankful to all of them who directly or indirectly helped me to come up this position. With a deep heart, I should thank all the student friends who are present here. I'm really happy, and I thank all the staff members who are with me in my journey in this institution, and they made me what I am here. Thank you, one and all.
Thank you, sir. I request Dr. M. Victor Anthony Raj, President LPA, to propose the vote of thanks.
Good evening, everybody. Already, sir has made my job simple. He thanked everybody the successful conduct of this first endowment lecture. On behalf of Loyola Physics Association, it's my duty to thank everyone present here. Everyone wrote for the successful conduct this first endowment lecture. I thank the speaker for spending his valuable time to exchange knowledge for this younger generation, because knowledge sharing is an important process in growth. So next generation growth really lies on the sharing of knowledge. Sir has done an excellent job. So I once again thank our speaker Sunil Verma for this wonderful job delivering the first endowment lecture. I thank the management for supporting us. I thank the dignitaries, Dr. P. Saharaj, Research Professor, Director, Data Center, Dean of Research, Dr. J. Madhavan, our faculty, one of our faculty member, always tirelessly working for the growth of the institution and growth of the college. Then I thank all the department faculty members for their support and non-teaching staffs for arranging all the functions, especially our beloved non-teaching friend, Mr. Arokyam, throughout this lecture. He has done a wonderful preparation to deliver this. Then this first lecture is live streamed in YouTube. So this YouTube live streaming is done by our Viscom team, LAMP team. For that, I thank our LAMP team leader, Mr. M. Adekalasamy, Senior Technical Instructor, and LAMP team members, Mr. Selva, Mr. Riteshwaran, Mr. Gabriel, Mr. Anbu Arasan. So all these people have done a wonderful job to live stream this first endowment lecture of Dr. J. Jerome Das. Once again, I thank the LAMP team. I thank everybody, student friends, research scholars, everyone for attending this function and making this function a wonderful one. Thank you one and all. First endowment lecture of Dr. S. Jerome Das. In a special way, we would like to express our gratitude to Father Rector and Father Principal, for Secretary, for having supported us in this endeavor. Coming to Dr. Jerome Das, he is one of the pioneers in the department who has motivated young researchers to do research in this department. If you look into the list of students who got graduated from our department, vast majority of them are first generation learners. Whether it is my student or Dr. Jerome Das students, they are all, majority of them are first generation learners. So in a way, the lifestyle of several students changed because of the research attitude built up at Loyola College. So in this aspect, we salute Dr. Jerome Das. Certainly he is one of the legends in this college. We promoted research activities in this campus and we wish him all the best. And as Dr. Sunil pointed out, we will be all there for the 50th examination of his candidates. So thank you very much.